Hi everyone. Today we're doing a A2 mechanics paper. Okay, so we start with the first questions about this projection of a particle. So whenever they're talking about these situations, you know the only forces acting on the particle is the force of gravity. So that's the only, unless they say that there's a force acting in the x direction, truly the only force is acting in the y direction. So what does that mean? Well, it means that the x component of the velocity, so Vx, has some initial value, V0, which is at time naught, and it never changes. At time 0. So it's always the same. So in this case, if we think of our particle being projected like so, and at this instant there's some angle theta that it makes with the ground, and the hypotenuse of this is V, big V. So therefore, the x component must be V cosine theta, and the y component, V sine theta. So our initial x value, which is the same as our x velocity for all time, is big V cosine theta, and that does not change. Now, what about y? Well, we know that if you look again at this diagram, at an instantaneous time, you make this angle and you travel some small distance in the x direction and some small distance in the y direction. And you see that the tangent of theta is dy dx. Now we can write this as dy dt over dx dt. Wait, you know what, actually? Yes. So this is going to be equal to, so dy dt is, there's a constant acceleration, right? So vy of t is the initial vy velocity, which is v sine theta, minus gt. So that's what goes on the top here, right? This is dy dt, which is just the vy of t over vx of t. And this is equal to v sine theta minus gt all over v cosine theta. So this theta is our 30 degrees, right? This is our theta naught, our initial theta, not the theta later on. Obviously later on maybe it's traveling like this, it's a much smaller angle. So in our if we put that our angle is 30 degrees, we have this triangle, or you can just put it in your calculator, that's good too. So the tan of theta, which is, so this is the tan of theta naught. No, it's the tan of theta as a function of time. So this is the general tan of theta. So we get right, so that the instant 2 seconds after projection, we have an angle of 15 degrees above the horizontal. So the idea is that, dy dx, the thing on the top changes. So this is true for all time. Sorry, I should have made that clear at the very beginning. But this theta is sort of as a function of time, and it's allowed to change. Whereas the theta here was the theta naught, the 30 degrees. So we have that sine of theta naught, which is sine of 30 degrees, is 1/2. So we have big V over 2 minus gt over v cosine theta, which is square root 3 over 2. And now we're told that at 2 seconds, so t is equal to 2, and theta is equal to 15 degrees, what is, we'll use that to work out v. So this thing is true for all time, so we're told that if we plug 2 in here, we should get 15 degrees there. And if you just plug all that in, so you can solve for something like v is equal to 2 times 2 over square root 3 tan of 15 plus gt, I think. And this will give you the correct answer. So what did we do? Even though my notation was a bit bad at the beginning, I apologize for that. We recognized that Vx is constant because there is no force acting in the x direction. Therefore, there cannot be any acceleration in the x direction, which obviously means that Vx is constant. And Vy is that Vy only affected by gravity. We realized that at any moment, dy dx at some time t, at any moment t, dy dx some time t is equal to tan of the angle at that time. So whatever the angle happens to be at that time, maybe here is at the beginning, here is it later. And then this is actually the chain rule that we used here. And then we plugged in the values. Okay. Question 2. So this one is all about moments around a point. So we have this cone, and it is being held sort of in this very uncomfortable looking position by a force acting over there. So we're told that it's an equilibrium, so it cannot be moving. Therefore, firstly, all the forces must be balanced. But an easier way to deal with it in this case is knowing that it's not turning around this point P. So any moment, the moments must balance. The moment is kind of like, the torque, the turning effect of various forces. So we've got F acting up here, and we've also got the weight of the cone acting at some point here. So it's the weight always acts on the center of mass. So where's the center of mass? Well, obviously the cone is completely symmetric around this central axis. We're told that F acts along the axis of symmetry, so that this line here, the 0.8 meters, is definitely through the center of the cone. So the center of mass must be somewhere along this line, because that's at the center of the cone. But it'll be somewhere. It's not going to be right slap bang in the middle. That would be a mistake to assume, because there's more weight at the bottom, right? So it's actually going to be shifted a little bit further towards the bottom. Well, if we look, if we just consult the formula booklet, we'll see that it's 2/3 of the way down from the vertex. So it's around here. So that this is 0.6, and over here is 0.2. So now we're going to think about the definition of the word moment. So the moment of some force F about some point P is the magnitude of the force times the perpendicular from P to the line of action of F. So this line of action. So F, we have two moments. So we have the F, this force F is sort of rotating the thing that way, and mg, which is acting down here, is rotating things that way. So what is the distance from F? Okay, so by the way, we're answering this first question. So I'm going to do it over here because we can look at the diagram. So this is question 1I. So the distance from P to the line of force of F, well, that's just the distance from here to here. And okay, so that would, sorry. Okay, so I am getting ahead of myself. I'm answering the next question. They just, for the first question, they only want the moment of the mass, and then we'll find the other moment in a second. So what is the distance from P to the line of force? Well, this is the line of force of the weight, right? Do it in green. So what's the distance between P and that? Well, it's just this horizontal distance here, right? And that's the same as this distance here. So it's this sort of completely horizontal distance. That's a right angle. Well, we can work out very easily that this angle is also 30 degrees. So how do we know that? Well, we know that that this is a right angle, so this must be 60 degrees. Therefore, this must be 60 degrees because it's a cone, it's symmetric. Therefore, that must be 30 degrees. So, so what is this distance? Well, the hypotenuse of the triangle is 0.6. So the distance from P to the center of mass is 0.6 sine of 30 degrees, which is 0.3 meters, because the sine of 30 degrees is 1/2. So what is the moment? Moment of the weight about P. Well, that's just equal to this distance, 0.3, times the magnitude of the force, which is, okay, so this is just mg, which is 20. So the whole thing is 6 newtons as required. So that's done. Or 6 Newton meters, sorry, because it's a moment, not a force. Okay, so now the next one that it's asking us to find F. So they want us to evaluate what F is, and then we have to set it equal to 6 Newton meters, because that's what it needs to balance in order to stop the cone from toppling over. So what is the distance from P to the line of action of the force? So this is going to be the radius of the cone. Well, if we look at this triangle, that's 0.8. So this is the triangle sort of cut through a section of the cone, and that's 30 degrees. So what is this R? Well, you can see that the tan of 30 degrees is R over 0.8. So R must be 0.8 tan of 30 degrees. So we know that, therefore, F times 0.8 tan of 30 must be equal to 6, because they balance. They're both going in opposite directions. So therefore, F is equal to, and I'll just make sure I've got this correct. It's equal to 6 divided by 0.8 tan 30. Yeah. So F is equal to 12.99 newtons. So I think that's all pretty self-explanatory. It's basically trigonometry for this question and knowing how to work out a moment around a point. Okay. So now we've got basically a rotation, a string elasticity question. So the King equations for these are T is equal to lambda over Lx, and E is equal to lambda over 2L x squared, where lambda is the modulus of elasticity, which is this 28 newtons. L is the natural length, which we're given, and x is the amount that it's been distorted, so the extra amount that it's stretched, or if it's compressed, the amount that it's compressed. So whatever the difference is between the natural length and what its length in the problem is. So here we have something suspended from the string. So there's a tension acting upwards, and there's the mg acting downwards. So when it's in equilibrium, so before it's given any kick, what do we have? Well, we have that the tension must be equal to mg because it's not moving, right? We can therefore solve for x. mgl over lambda, which is 0.2 meters. So we know what the initial displacement was. Then we give it this kick. So now we can use conservation of energy. So when you give it the kick, what energy is in the system? Well, we already have some elastic potential energy. So we have the energy elastic, and that's going to be equal to lambda over 2L x squared, and the same x that we had before. But we also have some kinetic energy. And this kinetic energy is 1/2 mv squared. So this is our initial energies. Now, what happens when the string goes slack? Well, so this is 1, and then afterwards you have the string slack. So the elastic energy is 0, because that's what, the string is slack. It's at its natural length. So lambda, so x is 0. So there's no deviation from the natural length. So this whole thing is 0. So elastic potential energy is 0. You have some kinetic energy, 1/2 mv prime squared. And you also have some potential energy. So this is equal to mgh by the usual formula. Well, what is h? Well, h must be x, right? X, because it was originally stretched by x, and now we've gone to a situation where it's just, so this was L and this was x. That's what it was at the beginning when it was down here. It had this extra bit x, and now it's not being stretched at all. It's just at its natural length L. So therefore the height that it has changed, the height that's gone up, the potential energy that's gained, it depends on x. So we set these things equal. So we have, lambda over 2L x squared plus 1/2 mv naught, v initial, squared is equal to 1/2 mv prime squared plus mgx. So we've got lambda, we've got L, we've got x, we've got x, we've got m, we've got v naught, we've got m, we've got g, we've got x, we've got everything, and we can therefore solve for v prime. Not too difficultly. Okay, so question 4. This one is about centers of mass, and they're basically relying on that you should know that the center of mass of a composite object like this one, even if it's a single object, you can break it up into composite pieces. The center of mass of a composite object can be found from the centers of mass of the components. And the formula for this is m total times, and this is a vector, x center of mass, so it's going to include, all the coordinates, is equal to, m1 x1 plus m2 x2 plus, all the component pieces. So in our case, we're going to call, we're only looking for the x component. So we're going to throw away the y bit, and we're just going to look at the x. And our 0 is going to be this line AB. Well, where's the center of mass of the rectangle? we know it's going to be right in the center there, right? So it's going to be 0.2 away. So say X rectangle is just 0.2 meters. What about the triangle? Well, the triangle looks like so. And you know that the center of mass of a triangle is the point where, so this is, if you mark out the midpoints of all the sides, and then from each midpoint draw a line to the opposite vertex. This place where they meet will be the center of mass. Well, for the triangle, so the triangle sitting, it only starts 0.4 meters away from our 0 line, so it's already 0.4 meters. So what is this distance? Well, we know that it's actually 1/3. So we know from our knowing about triangles, it's 1/3 of the way along this line, and also 1/3 away along this line, and 1/3 away along this line. So the distance from here to here is 1/3 of this distance. Okay, I'll use another color. So it's if we call this distance, D, then we know this is 1/3 of D. Because if I have some random line going like that, and I'm 1/3 of the way up it, then I'm actually 1/3 of the way up the x component and 1/3 of the way along the y component. So I can just treat them separately. So now this is 1/3 d, and what is d? Well, d is half of the 0.4, which is 0.2. Oh wait, silly me! I'm doing the y components. Well, that's really silly. This is not d. Whoops, forget that. Instead, I'm talking about this distance, obviously. So this is d. So it's going to be 1/3 of this line here at the top. So it's 1/3 of 1.8, which is 0.6. So this means that x triangle 0.4 plus 0.6, which is 1. Okay, great. Let me just get rid of this. So what next? Well, we have the x components, so now we need the masses. Now, in these problems, they don't really, you can treat mass as area. And the reason for this is that if I imagine that I have a mass unit area, we only need to worry about area because we're doing cross-section, mass per unit area lambda, then I will have something times lambda here, something times lambda there, and something times lambda there, and any mass will have, the area times lambda, so times this density. So the lambdas will cancel out, you can just divide by them. So really, these masses are just areas in these problems. Well, what's the area of this, of the rectangle, and the mass of the rectangle? That's just equal to 1.6 times 0.4, which is 0.64. And the mass of the triangle is just 1.8 times like 0.4 all divided by 2, which is 0.36. And then if you add these together, total, you just get 1. So our equation looks like this. X center of mass is kind of like a weighted sum coordinates of the other two. That's the rectangle times the x coordinate of the rectangle plus the mass of the triangle times center of mass coordinate of the triangle. And you'll see that this is equal to 0.488 as required. Okay, so that's all good. We're happy with that. And you'll notice actually that the that the center of mass is therefore somewhere out here. So from distance from here to here is only 0.4. So it must be a bit further out. So it's sitting like that. So it's sitting somewhere along this line. We don't care about the y coordinates. We don't care where exactly it is. So they're telling us that there is this force T. This is part of the second question. There is this force acting here, and we're told that the system is in equilibrium. Now, if it was in equilibrium, maybe you would have one of two things happening. If, say, T was gone, then you would have this prism toppling. So where would it topple? It would move around F. So we're looking at two different cases here. So the first is one where the mass, the weight of the thing is sort of overcoming the tension. So in which case you would have some sort of rotation around F, and it would fall down like so. So this is our case one. Let's do that. Case one topples that way. So for this we need moments about F. Well, let me just redraw this quickly. And here is our thing, and here's F. And that's T is being applied there. So what is the distance between F and the line of action of the force? Well, this is, even though T only starts there, this is the line of action. So the distance is just the height of the distance from F to the line of action of T is just the height of this block, which is 1.6 meters. And what about the distance from F to the line of action of mg? Well, it's just this distance here, right? It's just whatever this distance is. And we know that the base of the thing is 0.4, and the distance of x center of mass is 0.488 from this line. So therefore, the distance mg is 0.088. So these things must be balanced. So therefore, we have that the tension. So the tension times dft must be equal to mg times d mgf. So the tension must be equal to 0.088 mg all over 1.6. So this is the case that where t is quite small compared to the weight. This is where the weight is just enough to overpower it, almost enough to overpower it and send the thing toppling that way. Now, what if T became too strong? What if T became so strong that it actually started toppling the block the other way? It overpowered the weight. Well, in that case, you would have a rotation in the opposite direction, and it wouldn't be around F. F would be lifting off the ground. It would be around A. So you know that if it's not doing that, the moments around A must also be balanced. So this thing we got here, this is the min value of T. Now case two, going that way, moments about A, well, the distance from A to the tension is the same. It's just 1.6. So from A to the line of action of the tension, it's just 1.6. And now the distance from mg, the line of action of mg to A, or from A to mg is this full distance here, 0.488. And you just do exactly the same thing. And this is going to be the max value of T. So if T gets smaller than this or bigger than this, it will topple one way or the other. Okay, question 5. So this one is, it's kind of quite similar to the one we had a little way before, but it's just like a little more complicated. So we're given y as a function of x. So we know that there is some small So yeah, so some ball B is projected, and then after that, it is only under the influence of the gravitational force, and it moves in some way like this. So the first question is saying show that B is projected horizontally. Now, what does horizontally mean? Well, horizontal. Oops. This means that the angle theta is 0. And remember from before that dy dx is equal to tan of theta, which is equal to 0. So therefore, here we have dy dx is equal to 2 comes down minus 0.1x. Therefore, at x is equal to 0, which is the initial point, you know, x equals y equals 0 is the initial point. At x equals 0, dy dx is equal to 0. So this means that theta is equal to 0, i.e. it's horizontal. Now they want you to find the speed of projection. So this is going to involve, you know, time derivatives, and it's a bit, you know, it's not really obvious initially what they require, because this thing is y given in terms of x. They're not both parameterized in terms of t. But we can go back again to what we did before with this tangent, right? Dy dx is the tan of theta. So if you remember, dy dx can be written as dy dt over dx dt. And we remember that that we have some initial velocity for x, and that doesn't change, because the only force acting is in the direction of gravity. So, oops. So we have this is going to be equal to Vy at time 0 minus gt over Vx at time 0. And we know that all of the velocity at the beginning is in the x direction. So this big G, V of projection. Actually, this doesn't help us because t is equal to 0. Okay, I'm going to come back to this. I actually made a mistake in my notes, and I don't want to spend too much time being all quiet while I fix it. Now, I think that, yeah, the problem here is that time is equal to 0. So obviously we know that this thing is equal to 0. So that's not really helpful for us. But you should be able to get this. Well, okay. Okay, we'll just go to the next one. I think we'll come back to this. So, find the value of y when the direction of motion of B is 60 degrees below the horizontal, and find the corresponding speed of V. Well, at this time, so the motion is like 60 degrees. So at this very moment, that's 60 degrees. So we have that the tan of theta is equal to minus 0.1x from before. So therefore, if theta is equal to 60 degrees, then we have that x is equal to minus 10 tan In fact, it's minus 60 degrees because tan is, that would be 60 degrees. But this is minus 60 degrees because it's below the x-axis. So this is equal to 10 square root 3. So at that moment, this is the value of x. Therefore, from our equation, which we have, y must be equal to, and you just plug it into the equation, minus 15. And therefore, we can now look at the forces acting on the particle. So we have that the acceleration in the y direction is just equal to g, because that's the only force acting. So this is dvy dt. So therefore, we have that, well, from our constant acceleration equations, we can easily get this. Vy is gt, which you can say is y dot, is another way of expressing it. Dx dt, well, dx dt is just dx dy dy dt, which is dy dt over dy dx, which is gt over minus 0.1 x. Okay, good. So therefore, if we take these things and look at b, we get that, so we have our x, we have now that x dot, this is x dot is equal to minus gt over the square root of 3 from this equation. And we have just plugging in our x, because our x was well, it's over there, and this is also equal to the v cosine of 60 degrees, which is our the x component of our velocity at this time, this guy. Now we can also talk about y dot. So y dot is going to be equal to square root of 3. So y, okay, sorry. We have at this point that y is equal to minus 15, and if we plug that into our, if we think of that in our constant acceleration equation, 1/2 gt squared, we get that the time is equal to the square root of 3. Does that make sense? So our equation, constant acceleration equation is, y is equal to y initial plus y dot initial times time plus 1/2 acceleration time squared. So we know that the time that this happens is the square root of 3 seconds. So this gives us that y dot is equal to square root of 3g from this equation. The dot notation, if that's confusing, that just means that, if you have some quantity q dot, that's just equal to dq dt. It's just a shorthand. Sorry, I should have clarified that before. Okay, so we've got x dot, we've got y dot, and the speed is just given by, so the speed v is just given by the square, it's the Pythagoras, right? X dot squared plus y dot squared. And if you do that, you get the correct answer. Okay. So that was a little tricky, I guess, because it's got kinematics and stuff, and you were given this kind of weirdly non-parametric equation, but things do follow from the just from remembering that the acceleration is constant. Sorry. Okay. Question 6. So OA and B are 3 points on a straight line. Blah blah blah. And we have some particle P heading in that direction. And we have some force, the only horizontal force, is acting also in that direction. And we're given its magnitude. Let's just call it F for now. So we're told that this F has the value 0.4 v square root of v to the 1/2, and that so it depends on the velocity. So what is F? Well, F is ma, which is m dv dt, and we can use the chain rule. So this is going to be m dv dx dx dt. Well, dx dt is just v, right? So this is mv dv dx, and we know that the force is equal to 0.4 v to the 1/2. So that now we're required to integrate. So if we take all the v's on this side, we get m v to the 1/2 dv is equal to 0.4 oh wait, we're not required to integrate yet. In fact, we just divide. So this thing will just lead straight to that if you plug in the mass. Now we're going to integrate. So we initially have that 3v to the 1/2 dv dx is equal to 2. So we separate variables. We get, so I'm just going to put the numbers on the side for reasons which might become obvious. V to the 1/2 dv is equal to 2 dx. Now I'm going to integrate these, and I'm going to choose, or not 2, 2's gone. So the whole idea of, you know, when you usually integrate something indefinitely and you get a constant, and then you plug in the condition that you're given, and then you get kind of out what the constant is. Well, it's completely equivalent. So indefinite integral plus constant. That method is completely equivalent to just integrating between known limits. So I'll show you what I mean. You could just integrate this indefinitely and then plug in just make sure you add a constant and then work out what the constant is. That's perfectly valid. But I always prefer to do it a bit quicker. And I'm saying that I'm going to integrate this from when v was 1. So our boundary condition here is that when x is 1, v is 1. So my lower limit is when v was 1. At that point, x was also 1. So that they have to match. And then I'm going to be integrating to some value at some later time t. So we v of t, at which point the position is x of t. And who knows what that is. So what is the integral of this? Well, you know, these things with the square roots, you can usually recognize what they are. It's going to be v to the 3/2. And then that 3/2 is what came down. So we just take away that guy between 1 and v of t. And that's just equal to x between 1 and v of t. And so you see that v of t minus 1 to the 3/2 minus 1 is equal to x minus 1. Minus 1's cancel. So you get that v is equal to x to the 2/3. Okay, so now we're going to apply this. And we're told that the distance AB is 7 meters. So we know that v is equal to dx dt, right? And we've just found out that this is equal to x to the 2/3. So again, we separate variables, and we say that x to the minus 2/3 dx is equal to dt. And now I'm going to integrate these. And my lower limit, I'm going to choose as the time when x was 1. So I'm going to choose it to be the point where x was 1, and I'm going to call that time 0. And I'm going to integrate until the time that it passes through. So that was the time it passed through A. It was a time 0, and the x position was 1. And now I'm searching for the time, this t, at which point it passes through B, which is the point where x is equal to 8. So I get, if I integrate this guy, I'm going to get x to the plus 1/3, and that 1/3 would have come out, so it becomes 3 between 1 and 8, and this is just equal to t. So this gives you that t is equal to 3 seconds. Okay. Question 7. So this is sort of a rotational motion question, although it's got aspects of, you know, the elasticity and stuff happening again. So again, we're going to use this equation, T is equal to lambda over L x. Now, our first question is asking us to find the tension in the string. Well, that's super easy because we know that it's a formula we've just used. T is equal to, write it again, lambda over Lx. Well, we're told that the natural length of the string is 2, and look, is 2 meters. So therefore, all the stretch is happening here, or rather, whatever length this piece is the amount by which it's been stretched. Because if it was up to the string, it would just have its end by the ring r. So what is this distance? Well, we've got theta, we've got an angle, so we see that that this distance here, d, is 0.4 cosine theta. Sorry, 0.4 over cosine theta, because the cosine of theta is going to be 0.4 over d, so switch around, 0.4 over cosine theta. So that's our x. So this is going to be equal to lambda over L, 0.4 over cosine theta. And we know our lambda, we know our L, and that gives us this, this expression. So now we need to find m. Now this comes from balancing forces again. So we have, if we're looking flat on like a slice, there's the ring R with the string going up, and here's our ball. Here's T, and this is angle theta. So in force, you know, sort of force thinking, what is this? What is the component of T that goes up? Well, that's just T cosine theta, right? And what else is acting on the ball? Well, we've got mg acting on the ball, but the ball isn't sinking into the ground and it's not rising up in the air. So these things must be equal. Well, we know what T is. So T cosine theta is just going to be 3. So the mass must be equal to 3 over 10, which is 0.3 kilos. Okay, show that the value of omega, so this is the number of radians per second that this thing does not depend on theta. So I'm going to go back to this diagram. And I'm going to now look at this component of the force, which is T sine theta, right? So this is basically the part of the force that isn't holding the ball, stopping the ball from sinking into the ground, or stopping the ball from moving downwards or anything. Because so the ball isn't really on the ground actually. It just has a constant horizontal level. So the idea about these things being balanced was just that it doesn't move up or down. So that part of the force is stopping the thing from going up and down. The other part of the force is sort of spinning it in the circle. It's making it move in the circle. So that's the centripetal force. So, force centripetal, well, this is equal to mr omega squared. This is sort of, you have to remember these things. And that is T sine of theta. So for this, we need to know r. So that was theta. And if we look at the sort of space triangle, it's the same one with that being theta. We know that this is 0.4. Well, what is this radius? From trigonometry, we can see that this is going to be 0.4 tan of theta. So if we then plug that in, we get that m times 0.4 tan theta omega squared is equal to t sine theta. Well, what was t? What was t? It was 3 over cosine theta. So this is 3 sine theta over cosine theta. Well, sine theta over cosine theta, that's just tan theta. So the tan thetas cancel. And we get that omega is equal to the square root of 3 over 0.4 times m, which is just 5 radians per second. So you see that it's independent of theta because the tan theta is cancelled. Okay, so now they want us to find the value of theta. For this, so if we look, I've actually missed a bit out, I think. So I might. So in the actual question paper, it says that it is given for one value of theta, the elastic potential energy stored in the string is twice the kinetic energy of P. So they've given you a hint of how to solve this. It's obviously going to be conservation of energy, right? Okay, here we go. Oops. Let's just put it over here. Okay. So this is the actual question. And they want us to find this value. Oops. So what is the elastic potential energy? Well, we saw this before, elastic. That's just lambda over 2L x squared. And we have everything here, right? And the kinetic energy is equal to, 1/2 mv squared. And we use the fact that v is equal to r omega in rotational motion to get 1/2 m r squared omega squared. And we're told that this is twice of that. So we found out before that x is equal to 0.4 cosine of theta, and that r was equal to 0.4 tan of theta. So let's plug these in. We get that lambda over 2L times 0.1, 0.0, well, anyway, 0.4 squared cosine squared of theta is equal to m times 0.4 squared tan squared of theta times omega squared. So the 0.4s cancel out. And we get, so tan theta, well, this is just equal to sine squared theta over cosine squared theta. Wait, sorry, x was 0.4 over cosine theta. I keep doing this. 1 over cosine theta. So you see the 1 over cosine theta's squareds cancel. So we get that sine squared theta is equal to, actually, yeah, lambda over 2L 2L m omega squared. And this gives you that the sine of theta is 1 over square root 2. So you probably recognize this, but your calculator will give you the answer anyway, theta being 45 degrees. And that is all there is to it. So I hope that was helpful. I'm sorry for some of the confusion during some of those questions. It just messed up my bad notation. And yeah, let me know if you have any questions about all of this.